Welcome to section 6.11. We're going to talk a little more detail about carbocations and their rearrangements. This is something that we touched on a little bit in section 6.7, I believe, 6.8 perhaps, 6.7, 6.8. But we're going to talk more about it in detail here because, strangely enough, like we talked about before, if you have a carbocation that is on a primary carbon, remember primary means there are two hydrogens, two hydrogens there, only one carbon-carbon bond, then what will happen very quickly is you have a hydride move over to form the other carbocation that is more stable on that secondary carbon. And this happens not only with hydrogens, but it can also happen with methyls. When it does happen with a hydrogen, we call this a hydride shift. And because it goes from a carbon from one carbon to one that's adjacent, we call this a 1,2 hydride shift. And it's called hydride because a hydrogen with two electrons, such as this, is called a hydride. You can also have a 1,2 methyl shift if you have a similar set of circumstances with a primary carbocation and a CH3 up here, or maybe two CH3s. We'll just have two like that. You can have one of these CH3s move on over to give you the following chemical. Where now you have a secondary carbocation that is much more stable. And like I said, this is a 1,2 carbon shift, or 1,2 carbon shift. Well, this is not carbon shift, it's methyl shift. Sorry about that. Okay, so we have these two possibilities for carbocation rearrangements. And it's important to know, if you have two options, which way to go. Because if you remember, we said that primary is much less stable than secondary, which is much less stable than tertiary, which is less stable than allylic, and that's much less stable than benzylic, or at least around the same stability as benzylic. And so let's say, for instance, we're looking at a molecule that has a carbocation here, and we have the opportunity to do a methyl shift over here, or a methyl shift over, or a hydride shift on one side or the other. So if we did a hydride shift coming this way, then what we would get is a secondary carbocation, which is pretty stable. Or let's say we used the other hydrogen, the methyl shift going this way, we would have, or sorry, a hydride shift. I keep saying methyl shift. A carbocation, which is a tertiary this time. The tertiary is much more stable, and so that compound will form preferentially. And similarly, you could imagine the same with methyl shifts, where let's say you had a molecule that was going to be, let's see, that had these two types of systems here. So you have two different hydrogens, or two different methyls here. you have this methyl group, and you have this methyl group here. If the one on the left does a methyl shift, a 1,2 methyl shift, then you end up with a secondary carbocation, which is fine. Or if you have the one on the right do that, then you have a much more stable allyl cation that you make instead, which is the preferential choice. So that's basically what we're talking about here in this section. Carbocations rearrange using either hydride or methyl shifts here. And based on the stability of the resulting carbocation, you can predict which way a carbocation might rearrange to. And we can use arrows to show that rearrangement. So this has been section 6.11.